Hi, today we want to do some portfolio optimization. This is based on the modern portfolio theory. And this time I'm using MathWorks MATLAB software environment because of the beautiful way that it has for with working with arrays. So I will start by creating a script here. I call it S1 and let's start coding. So the first steps, I clear the screen, clear the workspace, and load data 1. So I have two data sets here. The first one has four stock market assets, and the other one is the all weather example. I will start by the stock market. So we load the data set here. Then the assets that we have in this one are, the first one is AMD, then we have Netflix, then we have Apple, and also Google. Okay, so now let's plot the data and see what we get. Alright, so you see we got the four curves here, the four prices. Let me remove this command here. Now let's do some pre-processing, just a small one. So I will get the number of assets here, which will be that data here that you see has 4 elements by 15,040. And this is the number of assets, which will be the first number of elements, and the length of the data set, which is size of data but element number 2. Alright. Then what we want to work on, and our target here are not the prices themselves, but it's the changes in the prices. So I will define a matrix here and directly put values in it. So let's see. We want to have prices of today minus prices of yesterday. So here we get all the assets, but then we start from 2 and go all the way to the end, the length of that. And this is minus. This time we start from 1 and we go up to length minus 1. This is what we get for the differences. Alright. Then we can also put the gains, or which will be the mean of the. Okay. So let's run it and see, because I'm not sure about the m. Maybe I need to rotate t before passing it to the mean function. Yeah. You see here mean now has 1539 elements, but what I want to have in M is only 4 elements, which is the mean or average return of these 4 assets. So let's run it again, and you see here M has 4 elements, right? Okay, so the first step here will be to calculate the variances and covariances. First of all, I define the covariances matrix. It will be an n by n matrix. So we will have variances of each stock, which will be on the diagonal position 1, 1, 2, 2, 3, 3, and 4, 4, and then we will have the cross variances or covariances of each pair of the stocks that we have here. And by definition in mathematics and statistics, we can determine the covariance. So I will have 2 loops. I want to go from 1 to n, and in fact cover all the combinations of the assets. And for each loop, what we want to do is the multiplication of the all values minus the average return, then divided by the length of the data. But okay, in fact here we have a sample mode, so it will be n to minus 1. Let's write this. So we will have sum of e of I, all its elements. So let's say, for example, asset A and B minus its average, right? And I need some other parentheses here. Yeah. So now multiplied by, we want to multiply element by element, not matrices here. And here we will put the daily gains, but this time for J, all records, and then minus the average return of J itself. And now there you go. There you have it. We just need to divide this summation by the number of samples minus 1 because we're in sample mode. Okay, now let's see. Good. So we have these covariances here. This is the variance of Google itself, or sorry, AMD itself. Then we have Netflix, Google, and Apple and Google. And then, for example, here we have the covariance or the variance between AMD and Netflix, and the rest will be the same. So far we have good values, but then one thing that's bothering me is that here we have all these values in dollars. So we cannot compare, for example, see here we have 1.2, but then for Netflix we have 59, which means that we cannot easily compare them. So to normalize all of these values, we have to go back here. I will add parentheses. And then so we'll have price of today minus price of yesterday and divided by the price of yesterday. So we will normalize this D. And now if you run it again, you will see that we have these kinds of values. These values are very small because I made a mistake here. We need to divide element by element, not by matrix. And we also want to have annual returns, so I multiply covariance by the number of days in the working year. Alright, so let's try it again. Okay, so here you see, now we have variances and covariances which are comparable. So after that, what we can calculate is correlations. So I define the same size matrix n by n and I go through all of them. And for correlations, what we want to use here is a bit different from covariance. In fact, we use the covariance values to calculate our correlations, and correlation is just the same data but in a normalized way. So for each of these, we'll use covariance of I and j divided by square root of covariance of I multiplied by covariance of j. And this is how we normalize covariance and get correlations. Let's see. Okay, so there's a problem here because we need to get 1 on all diagonal elements. Okay, yeah, sure. We need to put I and I and j and j. Great. We have ones on the diagonal elements, which means the correlation between Google and itself, AMD and itself is 1, and then you see 30%, 37, 47, and 60% almost. So now we've calculated correlations and covariances, but our goal was to find a good portfolio. And a good portfolio based on these four assets, the question for us or the problem to solve is to find the weights of each of these assets inside the portfolio. So let's say you have 20% Google, 30% AMD, 10% Netflix, and 40% Apple. Just like this. So let's start looking for a optimum portfolio. And I will use a random function to generate random portfolios, but a lot of them, and then find the best one among them. So I will do 1,000 portfolios, and I want to store all of them in a parameter called portfolio, and I will size it based on n. And then we have four assets here, which means we store four weights. Plus, I want to store also the variance and the profit. So we have 4 plus 2, we'll have 6 columns here. Now I will do this. I will create a matrix, an array of the weights that I want. And here we have 4 assets. So let's say 4. And let's go through all our random portfolios. So from 1 to 1,000, I will generate 4 random numbers, and so here we have 4 random numbers, and each of them will be between 0 and 1. To get the weights from these random numbers, I will do R divided by sum of R. Alright, so we have 4 numbers here, then we divide each of them by the sum. So in the end, the sum of the weights matrix will be 1. Good. So to calculate the profit or the mean return of a portfolio, we don't have a complicated equations, just the weight average. So what you will get is sum of base multiplied by the mean that we calculated before, this m. I hope we don't need to rotate m. Okay, and you multiply it also by 252 days to get the annual profit. Then for variation, I think we'll need to do a loop. So we'll go through all pairs of assets and then determine their share of variation in the whole variation of the portfolio, like this. So we'll have j going from 1 to n, and we also have k going from 1 to n to cover all the combinations of assets. And each time we add their variations to the total variation. So for each portfolio we start from 0 and we start to add them afterwards. So the contribution of each pair of portfolios in the variation will be that weight multiplied by the weight of k multiplied by their covariance. So here this for loop is covering all combinations, AMD and AMD itself, and also AMD or Google with all other assets that we have. And now we want to store these two parameters that we calculated in the portfolio. So I will put the weights first, then I put profit, and then I will put the variation. So that's it. Now with this loop, we've calculated the 1000 random portfolios, and then we determine their annual return and the variance of the profile. So let's try it and see if it's good. Okay, we have a problem. Yeah, so it's base. Okay, good. So everything seems good here. Now let's go for optimization. We don't do a complicated thing here. We just find the one that has the most reward to risk or yearly return to standard deviation. We can call it like modified Sharpe ratio, because the Sharpe ratio itself includes the difference between the return and the risk-free return of the market. But here we don't have that. So maximum modified Sharpe ratio. To find that, we can use the max function of MATLAB, which will return us the maximum value and the index of it in the array, and the array itself will be the maximum portfolio, all records, but then the profit, which is column 5, and divided element by square root of variance or the standard deviation. And the variance is stored in column 6. Okay. Now it is Sm, and then a portfolio. Okay, let's see. Yeah. Okay, good. So here we have the shares, like 27% AMD. Then these four are the weights of these four assets here. The best one that we found inside our 1000 samples. So 27% AMD, 30% Netflix, 30% Apple, and only 11% of Google will give us around 0.48 for the annual return and 0.10 for the variance of the portfolio. Okay, so far so good. Now we can also add some visualization to this. So I want to plot the results. In fact, the correlations that I calculated here is not really used in the portfolio determination. So you can remove it if you have a lot of data, but don't really need it. So for each of these assets, I want to plot their position in the risk to reward or return to variance graph. So I will put plot covariance of I and I, and for the vertical axis we'll put n of I, and that's it. What we need to do also is to run the hold function, the hold command once, and then do the hold command also in the end, just to keep the graph open. Okay, it's not visible. Let's put some markers here. So I will put black X's for this. There you go. We have these 4 elements here. I will also put their names together to see what we are looking at. So I will add a text label, and the label itself will be coming from here. Okay, there you go. So we have these 4 assets here. You see Google is very inefficient here in terms of risk to reward, and perhaps that is why we get only like 14% compared to more values here. And what we could also do is to plot all these portfolios. So let's do it. I will plot variation on the x-axis and then profit on y, and as the marker let's put like green circles, and also want to have thicker lines here. Okay, good. And also in this case I want to plot the efficient one. So this will be portfolio I, and variation is on 6, and this will be portfolio index I, and column 5, which is a profit, and I want to put red X. Okay. There's an issue here. Yeah. Again. All right. So seems that I closed the plot too early. All right. So there we have it. Let's close this one. And let's see. So we have it's up 2 here. All right. Good. The only thing that's problematic here would be like this plot that we have. So we want to multiply this by 252 and also this one by 252. That is the reason why the plot was a bit weird. And here do we, yeah, so in profits we are already putting this value, we're multiplying by the number of days, so here we're good. Alright, seems okay now. And you see when you zoom in, this point is really located in the frontier, so this is, as you know, called the efficient frontier that we have. And this, for example, if you compare this point to Netflix, you have the same gain but much lower risk. And if you compare it to Apple, you have a little bit more risk but much higher return. This is the way that it's, this is why it is more efficient, and even compared to AMD it has perhaps like 60% the return, but the risk is 4 times lower. There it is. And the other interesting thing that I wanted to show you is this one. So data 2 here has 5 assets. And these 5 assets are the assets that correspond to a, a famous portfolio which is called All Weather portfolio of Ray Dalio. Okay, so what we can change is change this one to data 2, so we load the other one. I will comment this out, and then the first one is long-term treasury bills. Then we have the index of the stock market. We have the medium-term bills. We have gold, and the last one is what we have. I have added here is DBC, which is a diversified index of commodities. And in the original portfolio that's defined by Ray Dalio, this is like 40% share. Then for SPY, for the stock market, we have SPY, in fact, is S&P 500 index. We have 30%. We have 15% for the short term, then 7.5% for the gold, and 7.5% for the rest of the commodities. Let's see what we get. So we load the data, we have the asset names here. Everything here seems to be generic. This is the same like daily values. Alright, so here we need to change this because then our portfolio we have 5 weights plus the profit and variation, so 7 columns here. We want 5 weights here, and we want 5 random values. And here the profit will be column 6 and the risk column 7. Same here, we want to have the variation there and the return here. Should be okay, let's see. Okay, good. So here the distribution is a bit different because we have first of all one more asset, and then one of them here that you see the commodity is located down there, and it's changed the shape of the efficient frontier. But still you see the one that we find is right at the border here, so it is on the efficient frontier. But let's see the values that we found. So the efficient portfolio that we found here is around 27% long term, 32% stock market, 27% of short term or medium term T-bills. Then we have 11% gold and around 1% commodities. This is normal because what you see as the return of the commodities, you can also even see it here. It's negative. It's very small, but it's negative. So that's why. And another interesting thing to see here is that you see we have negative correlations now. And this is why this portfolio can be something that's stable and can ride through all the bad situations in the market and like scary moments. But then you see what we have here as the share or the weights of these assets is much different perhaps from what we have in Ray Dalio's All Weather portfolio. But this is not very strange. First of all, what we're using is daily data, and it's from 2006 up to now 2023, so 17 years. But this portfolio is something that has performed very well for in long term, so for sure it's based on data from a very long year for period. So this is finished. I hope it was interesting for you. We have more videos or trainings based on this subject coming.